I've got a submission here from 2dogrc who has a question about a flip out that his copter did. We're going to take a look at that. For those of you who don't know, 2dogrc is a sponsor of RC Groups and has a site where he sells all sorts of multi-rotor related, RC related things. Thanks for sponsoring RC Groups and for all you do for the hobby. Let's take a look at your log. So here's the moment in the flight that you're asking about. And I've got the motor traces up right now, and I also want to be looking at the sticks so we can see what inputs you're giving. And as you raise the throttle, it looks like you were doing a series of maybe flips or rolls, some acro moves. As you raise the throttle, we can already see that this yellow motor is running higher than the other three. So it would be quite normal to see, for example, the rear two motors spinning higher than the front two motors. That could be because of a CG situation or an aerodynamic situation. It's quite normal to see the copter be a little bit imbalanced front to back and to see the rear motors spinning faster or sometimes slower, but usually faster. Usually the balance of forces on a copter, in my experience, is causing it to have a pitch back moment. That means that the rear motors need to spin faster to counteract that moment. And we see a positive pitch I term as a result of that. But what is unusual to see is for the rear motors to be so significantly different from each other. One thing we could infer is that this back left motor is giving less thrust than the back right motor. Another thing we could infer is that the back left motor is giving the same amount of thrust, but the force on the copter is imbalanced such that there is not only a pitch back force, but also a roll left force, meaning that basically this back left motor needs to spin faster to counteract and balance out the forces acting on the copter. Now, I think that's relatively unlikely because our copters are generally subject to aerodynamic forces that are relatively symmetric across the roll axis, and they're generally, the CG is relatively centered across the roll axis. So I think that the most likely interpretation right here is that this back left motor is making less thrust than the back right motor, and therefore is needing to spin faster to achieve the same amount of thrust. Now, as you raise the throttle here, then the motor maxes out. And notice that these other motors all drop down to 0. Some people have asked, does Clean Flight maintain sort of a reserve of throttle? Does it save back the top 15% of the throttle so that if a motor saturates, you'll always have a little bit of extra throttle to maintain stability? And that's actually a really that's like how Multiweed did it. It's a really outdated way of handling motor saturation, which is when a motor goes to 100%. What CleanFlight does is when any motor hits 100%, the other motors are scaled down to maintain the right proportion of thrust between them so as to keep the copter stabilized. Okay, so we see that as soon as the back left motor hits saturation, the other motors immediately scale down to try to keep the copter stabilized. And notice that right here, and let's also bring up the gyros while we're at it. No, sorry, not the PIDs, the gyros. Now we can see that a yaw situation is developing. The yaw gyro is going up, and the pitch and roll gyros are going down. So the copter is beginning basically to tumble. It's spinning. This motor is maxed out. The copter is trying to stabilize the situation by spinning these motors down. It knows that it shouldn't stop the motors entirely. There's only so low that it's going to bring them. The gyros indicate that the motion is getting worse. It's getting faster. These traces are getting taller or more negative. And now you cut the throttle and you've given up. You've decided that we're done now. Okay. Now notice, in this situation, now we have two motors at saturation. One motor is saturated at the top end of the scale, and the other motor is almost completely shut down. At that point, you have fully exceeded the dynamic range of the copter. In other words, the copter needs more authority than it can possibly have. The most authority the copter could possibly have is one motor is at full and one motor is at 0. It cannot generate any more rotational authority than that. And when you hit that scenario, which you basically have now, it's all over from there. And the copter tumbles and tumbles and tumbles and hits the ground. Okay, so we've analyzed the situation. Now, what happened? I have a theory about what happened. I'm gonna let's look back at your motor traces a little bit because I think we're gonna see that this problem developed earlier than you realize. Right here, notice that here we also have the back left motor running hotter than the back right motor. And here. Whereas notice that the front motors are pretty much running at the same speed. Here we're doing some maneuvers, so there's not a lot we can draw from this because we can't tell whether the motor is doing the right thing or the wrong thing. But when we're in sort of straight and level flight, we can assume that the motors, the front and the back motors, should be roughly moving at the same speed. And they're not. Same thing here. I have a theory that if we go back far enough in this trace, I wonder if this problem developed over the course of the flight and whether we would see that the traces come together earlier in the flight. I'm noticing here that this motor is peaking off the top of the chart. It's saturating. And notice that as soon as this motor saturates, all the other motors drop back out, right? The red and the blue motor immediately cut. And so again, we've got a scenario where that motor is starting to saturate. We've got some surging here between the two back motors are sort of oscillating here. Let's go all the way back to the beginning. Yeah. Oh, yes, yes, jackpot. Okay, this is what I said it earlier, this is what I was hoping to see. At the beginning of the flight, notice that the back two motors are roughly consistent with each other. Their lines are roughly together, and then as we move forward through the flight, I think we should see that they begin to diverge. See, they're together. The red and the yellow lines are together. Here we are in forward flight again, just normal flight. Don't look at the acro moves where things are going crazy and you're maneuvering. Can't really judge much from that. Here they're together, seeing some surging here. This may be where the problem started to happen, because notice that they're surging out of sync with each other. One is going up and the other's going down to kind of counteract it. We're doing some moves, Here we see that the motors are saturating, but you're in the middle of an extreme move, and so that's not necessarily a problem, although do notice that you're doing a left roll, and now this is where you're ending the roll and the stick is returning to center. Notice that this motor has spun harder than this motor. So the problem may be beginning to happen now. No, still roughly together. Maybe the problem is only coming out on the really extreme moves. Still together, still the yellow and the red trace are still together. Maybe they starting to diverge here. The yellow trace may be starting to diverge here. Yes, possibly. Yes, see the yellow trace is now slightly higher than the red trace. That motor is having to spin slightly faster to get the same amount of thrust. Now they're starting to diverge for sure. Back together, but still slightly higher. The yellow is slightly higher. Back together. Okay, and yellow is slightly higher. And as we go through, okay, now they've clearly diverged. So it was like right about here where the problem, maybe this twitch right here is where the problem happened. Well, I think what we may have here is a scenario where the problem is sort of coming and going, but we can see that toward the end of the file, we have this yellow motor being higher, which means it's generating less thrust. And what is the cause? My best guess is going to be that you had a loose prop. That's my guess. And that prop slowly worked its way loose over the course of the flight until finally it just gave up the ghost right here. That's when the prop actually went loose. The motor stopped generating thrust. Because the motor stopped generating thrust, clean flight sent the motor to maximum. because the less thrust the motor generates, the more throttle signal clean flight will give it. The PID controller is trying to compensate for the lack of thrust. Of course, when there is zero thrust, the motor goes to max. The motor is still not making any thrust. Clean flight then reduces the other motors to try and get the balance correct, and that can't happen. And then the whole thing just goes crazy. If it wasn't a loose prop, my next best guess would be some kind of a failure in the motor or the ESC that was causing it to slowly lose thrust. But that seems less likely than a loose prop. So I'm going to go with loose prop on this one. Regardless, it's pretty definitive that we can see that there's this problem that develops over the course of the flight where this back left motor is making less and less thrust. And we can see that because during stable flight conditions, like here, over the course of the flight, we can see that motor being sent a higher and higher throttle signal. And we know that during stable flight conditions, we should see roughly the same thrust between the back two motors, because that's just how things usually are. We don't see a scenario where throughout the entire file, this back left motor is higher. And that's why I say that the problem developed over the course of the flight. And then there's just this moment where it lets go. So the thing I would ask you to take from this is that whenever you see a motor going to maximum, it means that it is being asked to generate more thrust than it's capable of generating. And one reason that might happen is that you have a low power system. If you have a 2S copter, for example, I think you're going to see that a lot more often. If you have one of the powerful 4S copters with, an 8-to-1 thrust to weight ratio, like many people are flying these days, that's less likely to happen. But then the other thing you could look at is some kind of a mechanical situation that is causing the motor to not generate as much thrust as it could, such as a loose prop, maybe a bad bearing. The thing is, a bad bearing, I don't think a bad bearing would develop like this did and then just suddenly let go. Anything's possible. But a loose prop that's sort of slipping and slipping and slipping and slipping, and then finally just, that's it, your nut comes off. That's exactly what I think this would look like. Whether that's what actually happened or not, I don't know. That may sound kind of questionable, but I actually had a scenario just last weekend where I had put my props back on from working on my copter, and I just hand twisted the nuts on so I wouldn't lose them, but I didn't actually get out my wrench and tighten them down. And then I got to the field, and I just started flying. And then, 2 minutes into my first flight, I dropped an arm and the copter went into the dirt. I was like, what the heck happened there? And the answer is that all of the prop nuts had been completely loose and the props had just been flying based on friction. And it was only when I jammed the throttle to try and climb over an obstacle that one of them finally let go. But I had been flying for 1 or 2 minutes, just cruising around, getting my first battery in before that even happened. So, I mean, you could just totally fly on loose prop nuts just off of friction, depending on how tight your props fit your shafts. That doesn't sound right. Anyway, there you go. Hope that was helpful. Hope that was educational. Happy flying.